Okay, so in this video I will be finishing 12.3. I kind of cut off the last video because something was going on outside of my house, so I do apologize about that. So I'm just going to pick up where I left off. In this section of 12.3, I was kind of almost done with it, and so after I finish this, I'll go into section 13.1. So this video will be 12.3 and 13.1, or the end of 12.3. Okay, so at the end of that last video, we were talking about the identity matrix. And so I said that if you multiply a matrix A by the identity matrix, then this is like the same thing as multiplying a scalar by 1. So it'll give you back A. So that's why it's called the identity matrix. So in this example, they're giving us two matrices, A and B, and they're wanting us to find A times the identity matrix of a 2 by 2 matrix, which is this matrix right here. So that I sub 2 means the identity matrix of a 2 by 2, or a 2 by 2 identity matrix, I should say. So if I multiply this by A here, then to get the first entry in the result, I have to multiply the first row by the first column. So that would be 1 times 1 plus negative 2 times 0. So that'll just give me 1 there. And so forth. So to get the next entry, negative 2, I have to multiply the first row by the second column, and that would give me 0 plus negative 2, so that would give me that negative 2, and so forth. Just to remind you, A here is a 3 by 2 matrix, and this identity matrix is a 2 by 2. So I can multiply those two together because the insides match. And this does result in a 3 by 2 matrix. And in fact, if you keep going, we do see that this is equal to the original matrix A. So this shows that A times that identity matrix is still itself of A. Okay, so the second example wanted us to multiply the 3 by 3 identity matrix, so this matrix here, by A. So notice that they're asking us to do the 3 by 3 because it has to match with A in this order, which is a 3 by 2. So if I'm switching the order now and putting the matrix A second, then I have to multiply that by a 3 by 3 identity matrix so that the inside numbers here match. And of course, this would equal a 3 by 2 matrix. And let's just look at the first entry again of the answer, which is 1 here. And this is given by multiplying the first row by the first column in A. So the first row of the identity matrix by the first column in A. And that would be equal to 1 times 1 plus 0 times 0 plus 0 times 1. So that's just equal to 1 there. And of course you can keep going, but this is also going to give us A. Okay. And just one more reminder about the matrix multiplication. To get this entry here, negative 5, that entry is in the third row. So I would be using the third row of the first matrix, and it's in the second column. So I would be using the second column in the second matrix to multiply to find that negative 5. And you see that the first two entries are 0, so those will both be 0, and then the last two entries are 1 times negative 5, and so that is equal to negative 5. Okay, and then you can look at the rest. B times I, here's B, here is the 3 by 3 identity. This will in fact give us back B. And And that's it. I'm going to let you look at that one on your own. So the identity property that we just kind of showed is that if A is a n or m by n matrix, then the m by n of the identity matrix times A is equal to A, and A times the n by n identity matrix is equal to A. And if A is an n by n square matrix, then it doesn't matter which order you multiply it in, because I will be the n by n square matrix as well. Identity matrix. Identity square matrix. So it doesn't matter which order you multiply that in if it's a square matrix. It'll still give you A either way. Alright, so we are going to learn how to find the inverse of a matrix. And so if we have a square n by n matrix A, and there exists an n by n matrix denoted like this, and we read that as A inverse, just like an inverse function, for which A times A inverse is equal to the n by n identity matrix, then this notation is called the inverse of the matrix A. So the inverse kind of undoes the matrix and gives back the identity. Okay. And it will be in this exact order. So it'll have to be A times A inverse for it to equal the identity matrix. I'm sorry, it doesn't necessarily have to be in that order. I kind of spoke wrong. It can be in any order. So if I multiply A inverse by A in this order, it should still give me back the identity matrix if it is in fact the inverse. Okay, so for this example, it wants me to show that the inverse of this 2 by 2 matrix A is this 2 by 2 matrix here. So they want me to show that these two matrices are inverses of each other. And so in order to show that, we can multiply. We can show that A times A inverse and A inverse times A is equal to the 2 by 2 identity matrix. So here I have the matrix A, and then what they are assuming is A inverse. And if I multiply those out, the first entry here, 1, is in the first row, first column. So I would be using the first row of the first matrix and the first column of the second. So that would be 3 times 1, which is 3, plus 2 times -1, which is -2. And 3 plus -2 is equal to 1. And so forth. So the next entry is 0, and this comes from multiplying the first row by the second column, because that's in the first row, second column entry of the answer. And this would be 1 times -2, which is -2, plus 2 times 1, which is 2, and that would equal 0. And you can keep going and multiplying until we get the rest, and this is in fact the 2 by 2 identity matrix, since the diagonals are 1 and everything else is 0. And then you see that they do it the other way around and multiply it this way. And we still get the identity matrix, sorry. So the reason why the order doesn't matter here is because this theorem is for n by n matrices. of a n. I feel like this should say n by m. Oh no, that is n by n. Okay, just making sure. Okay. So we are going to go over the steps on how to find the inverse of an n by n matrix. So the first step is, if we have a matrix A, to form the augmented matrix like this. So this whole thing is a matrix itself. The A is going to be the matrix A, so the entries from matrix A. Then we're going to have the bar like we usually have in an augmented matrix. And then to the right of the bar, we will have the n by n identity matrix. And you'll see me do that in the next example. Actually, I'll go ahead and show you. This is what that would look like. So this is the entries from that matrix A up here. And then this is the identity matrix of the 3 by 3, the 3 by 3 identity matrix. And so this is that notation here. So that's the first step. The second step is to use row operations to transform this matrix into reduced row echelon form. Once we get it in reduced row echelon form, it should contain the identity matrix on the left of the vertical bar now. And the n by n matrix on the right of the vertical bar will be the inverse of A. So let's do an example. So they're giving us this matrix A, which is a non-singular matrix, and they want us to find the inverse. So just so you know, non-singular means a square matrix that is invertible. So non-singular means, a matrix that is invertible, which also means the determinant is non-zero. So we're going to see that in order to tell whether a matrix has a inverse, whether it's invertible, the determinant has to be non-zero. So they're just telling us that this is a matrix that has an inverse, and they're asking us to find it. All right, so we're going to start using row operations to transform the left side of this matrix into row echelon form, just like normal. But when we do these row operations, we're also going to perform them on the right side of this matrix. Okay, so the first thing I want to do is make sure this is 1, but it's already 1, so that's great. So now I can move to the entry below it and get this 3 equal to 0. So I am going to multiply row 1 by -3 and add it to row 2. I don't know why I highlighted only that part. I'm talking about this whole row 1. So I'm multiplying row 1 by -3, the whole thing, and I'm adding it to row 2 to get a new row 2. So the first entry will be 0. Second one, -3 times 2 is -6, plus -1 is -7. The next one, -3 times 1 is -3, plus 1 is -2. Next one, when we get to this one, this is -3 times 1 plus 0, so that'll give me -3 right there. And then the next one, I already do that one. Negative 3 times 0 is 0. 0 plus 1 is still 1. And then negative 3 times 0 is 0. Plus 0 is still 0. Okay, so we got all the entries below the first one to be 0 here. So far so good. Now we will divide the second row by negative 7 in order to get that first entry to equal 1. So this is dividing the entire row 2 by negative 7. So we will get a positive 2/7, positive 3/7, negative 1/7, and still 0. And now the last thing we need to do is get this entry to be 0. So I can multiply row 2 by negative 1 and add it to that 1. That'll give me 0. So that's what I'm going to do in the next slide. So I multiply row 2. Wait. Oh, reduced row echelon form. Okay. So reduced row echelon form means that I need to get everything else equal to 0 as well. So actually, they're not doing that step yet here. What they're actually going to do, so reduced row echelon means that you get everything else equal to 0 as well. So they want all of this equal to 0 and the diagonals equal to 1. So reduced row echelon really means get it as pretty much is getting it as close to the identity matrix as possible. So actually what they're going to do is they're going to multiply this row by negative 2 and add it to row 1 to get that to be equal 0. So that is what they're doing here. Negative 2 times row 2 plus row 1. And that gave them this new row 1. Okay, and then they will add a just trying to see what they're doing here. Oh, okay. And then after that, they will multiply negative 1 here and add it to this to get that to be 0 next. So that is what they are doing here. Use different color to get a new row 3. So they did 2 steps in that from that last slide, which is kind of cute. They did that. So they did get both of these equal to 0 in that step, which is good. So now what they're going to do is get this one equal to 1 by multiplying by that reciprocal. And I mean multiply that whole row by the reciprocal. So they are multiplying row 3 by negative 7/2 to get a new row 3. So that gets that equal to 1, and then everything else changes as well. And the zeros are just staying the same because we just multiplied those by number. And then finally, to get these last 2 equal to 0, we can multiply row 3 using this because we want to use this 1 here. Multiply row 3 by negative 3/7 and add it to row 1 to make that equal 0. To get a new row 1. And then the last thing they do is they multiply row 3 by negative 2/7 and add it to row 2 in order to get the last entry 0 there. So now the left side is completely in reduced row echelon form because each first non-zero entry is a 1 and everything below it and above it are equal to 0. So because we got the left side equal to the 3 by 3 identity matrix, the right side of this matrix here will be the inverse matrix of the original matrix we started with. So the inverse of A is this 3 by 3 matrix with the numbers from the right side of this augmented matrix that we got. And of course you can verify that this is the inverse by multiplying A times A inverse and A inverse times A to show that it gives you back the identity matrix, but it does. And you can even check this in your calculator. I've already showed you how to use your calculator to multiply two matrices. So you can always use your calculator to check your work. Okay, and you can also use your calculator to find the inverse of a matrix instead of doing that. So let me go back to this original matrix and I will show you how to do that. Okay, so I'm going to enter the original matrix A. So I go to second matrix and then edit, hit enter. And A was a 3 by 3 matrix, so 3, enter 3. And then the entries for A was 1, 2, 1, 3, negative, 1, 1, 0, 1, 0. Right? 1, 2, 1, 3, negative 1, 1, 0, 1, 0. So I've entered in my matrix A, and I'll go to second quit to get rid of it. And then go back to second matrix and click on enter for A. So we just entered that. And then we will click on second matrix again, math. And let me see, is it this button? I think it is that button if you just press X to that -1 button there and then hit enter. Yep. So this will give you the inverse of that matrix so you don't have to do all those calculations, but you need to still know how to do those calculations. So this, and then you can also go to math fraction to put that in those in fractions for you. Okay, so that is the same thing we got by doing it by hand. Okay, so this says show that the matrix A has no inverse. So first of all, I'm just going to find the determinant of this matrix, which would be equal to 2 times 6 minus -3 times -4, which would be 12 minus 12, which is 0. So because this determinant is 0, that tells me that there isn't a matrix. But we're going to still just show you how to do it this way as well. Or I'm going to show you how to do it this way. So again, to find it by hand, we set up this augmented matrix with the matrix A and then the 2 by 2 identity matrix. And we try to get the left-hand side in reduced row echelon form. So the first thing is we will divide the top row by 2 to get a new row 1. And then we can multiply row 1 by 3 and add it to row 2 to get that to equal 0. And that gives us a new row 3. Now notice here that all of these just zeroed out on the left. So therefore, this is reduced enough for it to be clear that the identity matrix cannot appear to the left of the vertical bar. So once I get, this is in reduced row echelon form because the first non-zero entry is 1 and everything below it and above it is equal to 0. But because it's not the identity matrix on the left, that shows us that it has no inverse. So if you can't get the left side to be the identity matrix, then it will have no inverse. Okay. So we are going to learn how to use the inverse matrix to solve a system of linear equations. So this system of linear equations can be written kind of as a product of 3 matrices. So the first, matrix A, will be the coefficient matrix. So this is the coefficient matrix, or the matrix that only has everything on the left, coefficients on the left. And then the constants on the right, this can be written as the constant matrix, or the solution, because it's equal to those numbers. And then this matrix in the middle is the matrix of the variables, x, y, and z. So this system can actually be written like this. And if I actually did this multiplication, a times x, here it would give me this, and then it's equal to the constant matrix B. Okay, so what's cool about this is writing this matrix in this equation form is if I can find the inverse A, then if I multiply A by this on both sides of this equation, wait, let me write it like this. If I multiply both sides of this equation by A inverse, and of course I have to do it on the same side, so it would have to be on the left side of both, then A inverse times A would give me the identity matrix, and that would just leave me with X, which is the X, Y, and Z, the variables. So the solution to the system would be A inverse times B. So this is how I can find the solution to the system. And they are kind of showing you that here. So here's the A inverse being multiplied on the left. And then we can use the associative property and multiply A inverse by A. And that will give us the identity matrix, the 3 by 3 identity matrix. And then the identity matrix times X is just X. And so the solution would be the A inverse times B. Oh. Okay, so I guess they already found. The inverse to this matrix over here. So I'm guessing that this, I don't know, they didn't really say that, but guessing that this is A inverse. And then they're multiplying that by the constant matrix. So if you did type this matrix A into your calculator and find the inverse, it would give you this matrix here. So now I'm taking that matrix and I'm multiplying it by the constant matrix because that's what x is equal to. And so using my matrix multiplication, this will give me the answer of 2, -1, and 1. So this means that x is equal to 2, y is equal to -1, and z is equal to 1. Okay. All right, so that is the end of 12 point, or I'm sorry, this was 12.4, wasn't it? I think I said 12.3 at the beginning, but my mistake. This was 12.4. And now we are going to go to 13.1. And I'm going to introduce sequences in this video, section 13.1. And then when we get back from break, I will shortly talk about 13.2 and 13.3, which is arithmetic sequences and geometric sequences. But I'll probably go ahead and put the PowerPoint up in the files just so you can have it there to look at. But I'm just going to quickly go over those two types of sequences when we return from break. Okay, so first of all, a sequence is a function whose domain is the set of positive integers, so starting at 1, and then the counting numbers. So the domain is only positive integers, whose range is a subset of the real numbers. So a sequence is usually represented by listing its values in order. The list never ends, as the ellipsis indicates, the 3 dots at the end. The numbers in this ordered list are called the terms of the sequence. And when we're dealing with sequences, subscripted letters are used, such as a sub 1 to represent the first term, a sub 2 represents the second term, and a sub 3 for the third term, and so on. So if you see this notation, a sub n, this means the nth term of the sequence. Okay, so one example of a sequence is this sequence here. F of n is equal to 1 over n. So the first term would mean we would just plug in 1 for n. So that would be 1 divided by 1, and that would give us just 1. Then the second term would be a sub 2, and that's just plugging in 2, so that'd be 1/2. And then 1/3, 1/4, up until n, which would give us 1 over n, the nth term. And there is that a sub n I was telling you about. Okay, so when a formula for the nth term, which is sometimes called the general term of a sequence, is known, then the entire sequence can be represented by placing braces around the formula for the nth term. So for example, this is a sequence that is going to give us the nth term for every single n that we plug in. So for the first term, we would plug 1 in for n, and that would be 1 plus 2 divided by 1, which would just be 3. And then the second term, a sub 2, you just plug in 2 for n, so that'd be 2 plus 2, which is 4, divided by 2, which is 2, and so on. So you can see the first 6 terms here that they found. And here is a graph of those first 6 terms that we just found. And you can see that this kind of makes a almost like a exponential decay, but not really, but almost. Okay, another example is the sequence that's given by -1 raised to the n power times n divided by 2. So to find the first term, b sub 1, I would plug 1 in everywhere I see the n. So that would be -1 to the 1 power times 1 divided by 2. So that would give me -1/2. That would be the first term. The second term, I'm plugging 2 in for n. -1 squared is a positive 1. 2 divided by 2 is positive 1. 1 times 1 is 1. And so forth. The third term would be negative because this now would be odd. It would be -3/2. The next one would be a positive 2, and so forth. And here is a graph of those. Here is when you plugged in 1, and then when we plugged in 2, we got positive. When we plugged in 3, it got back negative. When we plugged in 4, it was back positive. Plugged in 5, it went back negative, and so forth. Okay, so this is kind of like almost like a piecewise sequence. So it says that if n is even, you plug it into this first function or first sequence formula. But if n is odd, then you plug it into the second sequence formula. So for the first term, n would be odd because it would be equal to 1. So this would just be, I would plug it into the second sequence, which is 2 times 1, which would give me 2. And then the second term, I'd be plugging 2 in for n, which is even, so that would be plugged into the first sequence, which would be 2 divided by 2, which is 1. And then 3 is odd, so that would be 2 times 3, which is 6. I meant to use the other color. And then for 4, it's even, so 4 divided by 2 is 2, and so forth. And here is a graph of those points in that sequence. All right, so sometimes they are going to want us to recognize a pattern in a sequence and come up with the formula for the sequence ourselves. So for this first example, you want to look for patterns like, are we adding the same number to get from each number to the next? Are all these numbers a power of a number? Are they multiples of a number? So these are the kinds of things that you want to ask yourself. Are they changing signs, each number? So if they represent like if the sequence is all different powers of a number, like this one, all these numbers are powers of 3. So like this could be 3 to the 0 power is 1. 3 to the 1 power is 3. 3 squared is 9. and 3 cubed is 27. So we see a pattern because these are all powers of 3. So I know that the part in my formula will have a power of 3. And then I need to think about if n started at 1, what would make the first one equal 0 for the exponent? Well, that would be n minus 1. N minus 1 would be 0. And then if I plugged in 2, 2 minus 1 would be 1. So this would be the formula for that sequence. A sub n, the nth term, is equal to 3 to the n minus 1 power. Okay, the next one is going to be a fraction, and I know that obviously because these are all fractions and the numerator is all they all have a 1. So I know that my formula will have a fraction and the numerator will be 1. So then I look at the denominator. These are also all powers of 2. You might think they're all multiples of 2, but they skip a 6 and a 10. So it's not all the multiples of 2, because that would be 2, 4, 6, 8, 10, 12. It's skipping multiples of 2. But these are all the powers of 2 in order, starting with 2 to the 1 power, which is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th power is 16. And so these powers are just going up by 1 each time. And it starts with 1, so I know that that just needs to be to the n power, because the n will start at 1 and then be only positive integers. Okay, the next one doesn't look like any powers of anything, doesn't look like any multiples of anything. So the next thing I would want to look for is addition or subtraction. So to get from 3 to 5, I have to add 2. To get from 5 to 7, I have to add 2. And to get from 7 to 9, I have to add 2. But we have to think about the value of n. N always has to start at 1, and I need n within my formula. So if I start at 1, or if I have to use n equals 1 and I have to start at 3, then you kind of just have to play with it and see how can I get this to work out. So I know that 2 plus 1 is 3. And if I plug in 2, 4 plus 1 is 3. Or, 4 plus 1 is 5. 6 plus 1 is 7. 8 plus 1 is 9. And so forth. So this isn't exactly just adding 2 to each one. That is the pattern, but we also need to think about how can we start it with n equal to 1 and to get the first one to equal 3. So this would be 2n plus 1. And then the next one, 1, 8, 27, 64, 125. These are all cubes. Okay, these are perfect cubes. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. So these are all perfect cubes, and the base of each one is going up by 1 each time, and the 3 is staying the same. So this can just be n cubed because we would be starting with 1 and then going up. Okay, and then the last one, the first thing I notice is that it's alternating signs from positive to negative. So whenever you see a sequence that's alternating signs, that is going to include the -1 to the n+1 power in the formula right away, because that's what changes the signs. If I plug 1 in there, that would be 1 + 1, which is 2, so that'll give me a positive answer. And if I put a 2 in there, 2 + 1 is 3, that'll give me a negative answer. So okay. And then the other part, these are all multiples of 2. So that's where they get the 2n. All right, so you can play around. These are a couple of tricks on how to know which formula to use, and then you'll just want to play around and check to make sure they are working out. All right, so I have to introduce this factorial symbol because some of these sequences and series comes with a formula that we need to follow that will have the factorial symbol in it. So if n is greater than or equal to 0, and it's an integer, then the factorial symbol, which is written like this, in factorial, and that's how we say that. It looks like an exclamation mark, but we call it a factorial, is defined as follows. So 0 factorial is always equal to 1, first of all. And 1 factorial is always equal to 1. And n factorial is always equal to n times n-1 times n-2 times n-3, ... until we get to 1. So for an example of that, if I had 5 factorial, this would be equal to 5 times 4 times 3 times 2 times 1. And we would actually multiply all those numbers together. 6 factorial, same thing. We start with 6 now, and then we go down. So 6 times 5 times 4 times 3 times 2 times 1. So you start with the number that is here, and you multiply by all the numbers below it until you get to 1. Okay. And what this says is that n factorial is also is the same thing as n times n-1 factorial, which means, like, for example, this 6 factorial can be written as 6 times 5 factorial, because this whole thing here is 5 factorial, like I showed you. So 6 factorial is the same thing as 6 times 5 factorial. Okay. So a second way of defining a sequence is to assign a value to the first or the first few terms and specify the nth term by a formula or equation that involves one or more of the terms preceding it. So these sequences are said to be defined recursively, and the rule or the formula is called a recursive formula. So before, we had these formulas that maybe just had, n in it. So a sub n is equal to this. But now we're going to have formulas where maybe the previous term, n-1, is in the formula. So this is an example of a recursive formula. So the nth term would be equal to the n-1 term, so the previous term, minus 2 times n. So we could use the previous term and plug it in and find the next term. That is a recursive formula. So here is another example. So for this, they want us to list the first 5 terms of the recursively defined sequence. And here is the sequence that says that the nth term is equal to 4 plus the n minus 1 term. And they tell us that the first term is equal to 2. Okay. So I'm always going to be trying to plug in this previous term, the one they gave me, the first term, in for this notation. So the n minus 1 term, which means that n there would have to be 2. So if to find the next term, s sub 2, the second term, this would be equal to 4 plus 2. Because this, let me just rewrite it. This would be s to the 2 minus 1 term, which is 4 plus s sub 1, which is the first term, which they gave me. So this would be 4 plus 2, which is 6. And I should really write this horizontally so I can do all of them. Okay, let me use, that's a S, not a 5. All right, and then the third term will be given by 4 plus s sub 3 minus 1, which would be 4 plus s sub 2, which we just found to be 6. So this would become 4 plus 6, which would be 10. And then the next term, s sub 4, would be 4 plus s sub 4 minus 1, which would be 4 plus s sub 3, which would be 4 plus 10, because that's what we just found for s sub 3. So this would be 14. And then the fifth term would be equal to 4 plus s sub 5 minus 1, which is equal to 4 plus s sub 4, which is equal to 4 plus 14, because that's what s sub 4 is that we just found. So this is equal to 18. So these are the first 5 terms of this recursively defined sequence. Okay, so in this example, they're actually going to be using 2 previous terms in the recursive formula. So the nth term here is equal to the n minus 1 term minus the n minus 2 term. Okay, and this is whenever they will have to give you 2 previous terms in order to find this. So they say that the first term was 1 and the second term was 2. And so to find the next 3 terms, because they want us to find the first 5, so they already gave us the first 2. So the third term here would be given by u sub 3 minus 1, which would be u sub 2, minus u sub 3 minus 2, which would be u sub 1. And those have been given to us. So this will become 2 minus 1, which is equal to 1. So the third term would be 1. The fourth term would be equal to u sub 3 minus u sub 2. So that would be 1, because that's what we just found, minus 2, because that's what was given to us. And this would be equal to negative 1. The next term, the fifth term, would be equal to the fourth term minus the third term. And so this would be negative 1 minus 1, which would be negative 2. So for this sequence, they're always using the previous 2 terms and finding the difference between them. So the first term is always 1, the second term is 2, and then from there we're using the previous 2 terms. So the third term was u2 minus u1. The fourth term was u3 minus u2. The fifth term was u4 minus u3. So this is a special sequence called the Fibonacci sequence. And the terms of this sequence, these are called Fibonacci numbers. So it's actually a very, very famous sequence. You've probably heard of the Fibonacci sequence before. All right. So sometimes we might be asked to find the sum of the first n terms of a sequence. So that would be adding the first n terms together, like you see here. And rather than writing down all these terms, we can use summation notation to express the sum more concisely. So a sub 1 plus a sub 2 all the way to a sub n. This is the same thing as the sum. So this symbol here means the sum. A little Greek backwards, or not backwards. Yeah, no. Little Greek symbol that looks like an E, kind of. So that is the summation symbol. The thing below it where it says k equals 1, this is called the index, the starting point. And n, I'll say the starting point, that's what we start with. So we would start with plugging in 1 for k. And n is like the stopping point, where we stop. What's the last number we plug in for k? And then the expression here is the sequence. So this would be the summation of a sub 1 plus a sub 2 plus a sub 3 all the way up until a sub n. Okay, so this pretty much says everything that I just said. But this is an instruction to add the terms a sub k of the sequence a sub n, starting with k equals 1 and ending with k equals n, which is what I said. And this expression is read as the sum of a sub k from k equals 1 to k equals n. So here's a few examples. So to find this sum, we start with k equals 1, and I plug 1 in for k third. K cubed, sorry. So that would be 1 cubed, and then I go to 2 for k, so that'd be plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed all the way until n cubed. That's how we would represent that sum. This isn't us actually finding the sum, obviously, because they didn't give us an actual stopping point. This would be an infinite sum. Which is called a series. And the next one is another example where we're taking the sum of 4 over k terms, starting at 1 and ending at n. So this would be 4 over 1 plus 4 over 2 plus 4 over 3, all the way until 4 over n. Okay, so this one wants us to express each sum using summation notation. So we look at this sum, which is saying 2 plus 4 plus 6 plus 8 plus ... plus 16. So I know that it'll be stopping at some point because it has a stopping point, it has a starting point. These are all multiples of 2, 2, 4, 6, 8. So that tells me that the actual formula will be 2 times k here. And we could start at k is 1, because 1 times 2 is 2. And then you put in 2, 2 times 2 is 4, ... until we get to 16, which would be 2 times 8. So that's why the ending point would be 8. So that's how we can express that sum in summing or sum notation. The next one obviously will be the sum of 1 over some number, or sorry, over 3 to the power of k. That's pretty evident. Where k would equal 1, starting point at 1, and it's going to go up until n, because this is going all the way to n. So this was a finite sum, but this one is an infinite sum. Goes on forever. And so here is that answer there. Okay. All right, so here are some special properties of summations. So the first one says that if we have a multiple of the expression c times a sub k, then we can pull that c out front and have it be multiplied by the summation of just a sub k. So we can always pull a constant out front of a summation, which will be helpful to us a little bit later. And then the next one says that if I have the summation of a sub k plus b sub k, that I can break this up into the summation of a sub k plus the summation of b sub k. And I am not liking this. Okay. And the next one's very similar, except for it's minus. So the summation of a sub k minus b sub k would be the summation of a sub k minus the summation of b sub k. And the last one says that the summation of a sub k, where k starts at the j plus 1 entry, is equal to the summation of a sub k of k starting at 1 and going to n minus the summation of k starting at 1 going to j. So for example of that, which I was trying to think of, if I had k equals 3, so I'm starting this at 3, this is the same thing as k equals 1 minus k equals 1 to the 3, stopping at 3. So this would give you everything from 1 to 3, and we could subtract that from everything from 1 to infinity, and that'll just give us what's left, since it's the sum. And then the last thing is formulas for sums of the first n terms of a sequence. So these are some pretty common and special formulas that can help us determine the sum of a sequence, especially if it's infinite. Then we can use these formulas to figure out the sum. And I'm sorry, I meant to say finite, not infinite, if they're finite. then instead of writing down all the entries in the sum, then we can use the formula to find the answer to the summation. So the first one says that the summation of a constant c, starting with k equals 1 going to n, is just equal to c times n, because of course we'd just be adding c n times. The next one is the summation of k, starting with k equals 1. Well, this would just be, 1 plus 2 plus all the way to n. Well, this formula actually has a formula, which is n times n plus 1 divided by 2. The next one is the summation of k squared. And so this has a formula as well. And the last one is summation of k cubed, which is equal to n times n plus 1 all squared, or divided by 2, and then all of that squared. So the same thing as this one, but everything is squared. Okay, so we're going to find the sum of each of these sequences. So for the first one, we're looking here. The first thing I want to do is use that property that said that I can pull out this constant out front. Because the reason why is so that I can just focus on this, because this is one of my formulas that we just learned, the summation of k. And that formula was equal to, just rewrite that up here, it's equal to n times n plus 1 divided by 2. So the n here is equal to 5. So this will just become 2 times 5 times 5 plus 1 divided by 2. 5 plus 1 is 6. 6 times 5 is 30. 30 divided by 2 is 15. And 15 times 2 is 30. So that summation is equal to 30. The next one, the next example, is the summation of k squared plus 2. We're starting at k equals 1 and stopping at 10. So again, the first thing I can do is use the properties and break this up into two summations. Summation of k squared plus the summation of 2. And then I have a formula for the summation of k squared I'm just going to go back. That formula is equal to all of this, n times n plus 1 times 2n plus 1 all over 6. So n in this case is 10, sorry. So this becomes 10 times 10 plus 1 times 2 times 10 plus 1 all over 6. And then the next summation is the constant summation. So that would just be 2 times n, so 2 times 10. And so evaluating all of that gives me 405. The next example is the summation of k squared plus 5k minus 3, starting at k equals 1 and going to 24. So the first thing I'm going to do is separate this into 3 summations. Just by literally just separating them, everything else stays the same. And then I can use my formulas. So the one for k squared, wait, what changed? Oh, that's fine. So the one for k squared, n is 24. So that'd be 24 times 24 plus 1 times 2 times 24 plus 1 all over 6. The next one, they pull the 5 out front. So that gets multiplied by the formula for the summation of k, which is n times n plus 1 divided by 2. And then the last one is minus 3, the constant, so that'd be 3 times n, which is 3 times 24. So after evaluating all of that, you get 6,328 for that sum. Okay, and the last one had the summation of 3k squared starting at k equals 6, so this is new, and ending at 20. So to do this, first of all, I can pull out the 3, because that's a constant. And then I would want to separate these two. I would want to separate this summation into two summations so I can get k to be equal to 1 in order to use my formulas. Because I can't use my formulas if k is not equal to 1. They only work if k is equal to 1. So I want to use that property that says that this here in blue is equal to the summation of k squared, where k would start at 1 and go to 20, minus the summation of k squared of where k would go to 1 to 5. So sorry, I guess this was in, what did it say that was? Right, J. Okay, so I kind of said that wrong earlier, but this would be J plus 1, so J would be 5. So that would have to go 1 below, obviously, because we'd want to subtract all the 5 terms before 6. We want to include 6. Okay, so this is the first 5, the summation of the first 5 terms. And I want to start at 6. So I'm going to subtract all of those from the full summation of the terms 1 through 20. So now that I did that, I can use my formulas for the summation of k squared. So that's what you see with these two. And after evaluating all of that and multiplying it by 3, we get 8,445. Okay. And so I'm going to stop there for this section 13.1. And when we return, I will quickly go over 13.2 and 13.3, and then we will review for the final. Happy Thanksgiving.